very good morning, good afternoon, good evening my dear friends. Welcome to this TQM2 under the NPTEL MOOC series, and this is the 9th lecture or class we are taking. So, which is the penultimate or the second last class for the second week, and obviously after the 10th class you will have the second set of assignments. So, the first set of assignments because I did hear that what type of assignments would be given for TQM1 also, similarly for quantitative finance also, but it will be based on whatever is being covered. So, we will slowly expand our ambit and cover more interesting topics. So, coming back to the discussion of what the lecture we were basically discussing. In the 8th lecture, we basically discussed about ANOVA and how the effect of any factor or an experiment being done with respect to the numbers we are taking, how the average values are there, how the errors are there, what is the assumptions of the errors, and how any fluctuation in the mean of the so called means. Because if you remember, mu I is equal to mu plus tau I. So, that mean value is basically the mean of the means for all the processes. So, that will become clear as we proceed. So, let me continue reading it further. The above equations are called the one way or single factor analysis of variance model. So, obviously, if there are more like I, j, k, the variables are there, they can be two factor models and so on and so forth. Because there is only one factor is being investigated, it is required that the experiment to be performed in random order, so that the environment in which the treatment are applied, often called the experimental units, is as uniform as possible. Thus, the experimental design is completely randomized in design. Our objective would be to test appropriate hypothesis. What are the hypotheses? We will come to that later about the treatment means and to estimate them accordingly. For hypothesis testing, the model errors are assumed to be normal and independent, which I did mention about epsilon. The mean value was 0 obviously. So, let me read it further. Are assumed to be normally and independently distributed random variables with mean 0, as I did mention in the last class, and with a variance of sigma square, which means I am not putting any suffixes for sigma square, which I am assuming that the errors are not increasing and decreasing. They have a fixed value of variances, which is sigma square. So, the errors are independent of each other. This is very important. The variance sigma square is assumed to be constant for all levels of factors, as I mentioned, and there is no independency between the errors, because if that happens, obviously your whole concept will change. The above equations describe two different situations with respect to the treatment effects. First, the treatments or the A treatments could be a treatment could be specifically chosen by the experimenter. This can be the whichever treatment we are doing, it is 1, 2, 3, 4 till 8th one. In this situation, we wish to test the hypothesis about the treatment means, and our conclusions will apply only to the factor levels considered in the analysis. The conclusions cannot be extended to similar treatments that were not explicitly considered. So, if they have not been considered, obviously we cannot draw conclusions in those lines. We may also wish to estimate the model parameters, which are now mean mu only without the suffix, which is the average of the average. The word I am using in a very layman sense, but it will become clear to you later on. One would basically be the tau I, that is the fluctuations with respect to the mean of the mean, such that we can find out the means for each and every experiment or the treatment, which is mu suffix I. And obviously the errors, as I said, we have a mean value of 0, so that will not be considered, and we are also considering the errors are independent, they have a variance of sigma square. So, this is also the parameter of the model. So, this is called the fixed effect model, because the effects are fixed, kept to a fixed level, considering the sigma square are not changing. Alternatively, the treatment can be random samples from a large population of treatment. In this situation, we should like to be able to extend the conclusion, which are based on the sample of treatments, to all treatments in the population, whether or not they are explicitly considered in the analysis. So, hence here the tau i's are random variables, and knowledge about the particular ones investigated is relatively not of that importance for us. Instead, we test the hypothesis about the variability tau and what effects it has, and we try to estimate this variability. This is called the random effects model or components of variance model, which we will consider later on. Now, analysis of the fixed effort model, as I said. So, let yi represent the average of yi bar be represent the average of the observations under the ith treatment. Similarly, let y double dot represent the grand total, the average of the not the average, basically, yeah, in that sense, obviously it will be the average of the average of the total number of observations, and y bar double dot represents the grand average of all the observations. So, obviously, in that case, if yi dot would basically be the summation of yi and j summed up for all the j's, and yi dot bar would technically be the average of that would definitely be yi dot divided by n. So, here n is basically the observations which I have for each and every treatment, and then I will be able to find out the averages for y1 bar dot, y2 bar dot. So, that would 1, 2, 3, 4 would basically correspond to the treatment of the experiment change I am basically trying to do. Similarly, y double dot would basically be the sum of all the values corresponding to I and j, and the average of that would basically be the sum of would be basically y double dot divided by total number of observations which we considered as capital N. So, it will be the n plus n plus n, and how many such small n's are there? There are a small n. So, obviously, it is the grand sum which is capital N. So, here it is given where capital N is equal to a into n is the total number of observations. We are interested to test the equality of this treatment. So, hence the appropriate hypothesis is under H naught, which is the null hypothesis, which we technically, as I mentioned, we would like to disprove, is that all the means are equal, which is mu i's are all equal. Hence, it can be written as mu 1 is equal to mu 2 is equal to mu 3 till mu suffix a. With respect to the alternate hypothesis, that at least one pair are there where they are not equal. In this effect model, we break the ith treatment mean mu I into two components, which I have mentioned as mu I is equal to mu plus tau I. We can define this value of mu as the summation of which the summation of all the means divided by the number of treatments, which is sum of mu 1, mu 2, mu 3 to mu 4 till dot dot till mu a divided by a. Based on the above, we can conclude that basically that averages of the fluctuations which we have from the mean of the means is basically 0. So, hence the average of tau I is 0. This is important to note. Thus, an equivalent way to basically write the above hypothesis would be that all the taus are 0, that is tau 1, tau 2, tau 3 is till tau a is 0 with respect to the case that for at least one of the treatment tau suffix I is not 0. So, this is something to do with the mean, nothing to do with the variability of tau. So, it may be possible the mean values of tau are 0, but still there is high variability. The name analysis of variance is derived from the partitioning of the total variability into its component parts. So, obviously, the component parts would be two. One is the sum of the squares, which is basically sum of the squares. So, now I will highlight it in particular for your convenience. So, this is the sum of the squares which I mentioned. So, if you look here, it is basically you are trying to find out the differences of each and every observation from its grand total mean value, which is y bar dot dot in the suffix. That means you dot dot, the first dot means for all the experiment or the change of the etching which you are doing 1, 2, 3, 4 till a, and the second dot is for all the observations which are there under each and every a. So, if you find out the sum of the totals of the squares, so you add them up, square them up, add them for and sum them up for all the values changing from I is equal to 1 to a and j is equal to 1 to n. It is used as a measure of the overall variability in the data. So, in that case, if you expand that, this terms basically has two components. So, the two components would be this, which I am just highlighting for the second time. So, one is with respect to the differences of the mean values. So, what are the mean values? So, now I will basically highlight each and every observation carefully. So, the first part, which is now colored red, with respect to y bar I dot minus the y double bar y bar dot. So, basically it means that I am basically trying to sum up for each experiment, sum them up, considers the random variable and basically find out what is the difference from the average of the averages. That is part 1. Number 2, where I will again change the color in order to make it understand. So, this would be the individual fluctuations which are happening with respect to the average of that particular experiment. So, if you basically concentrate here this value, so which I am trying to now circle, that y bar I dot is basically the averages for any experiment, but for all the examples under that experiment being considered. So, the above equation, when we basically find out, it can be derived very easily. The above equation is basically the fundamental ANOVA identity. So, that sum of the squares have been divided into two parts. One technically can be considered as the error in the sample, and one can be considered as the error throughout the sample. So, it is basically something to do with the inter sample errors and in the intra sample errors, based on which you are trying to basically find out the over sum of the square of the errors. It states that the total variability, which is sum of the squares in the data as measured by the total corrected sum of the squares, can be partitioned into two parts. One is the sum of the squares of the difference between the treatment averages and the grand average, plus a sum of the squares of the difference of the observation within the treatment from the treatment average. So, basically one is between sample and one is basically compared with the sample. So, basically what I mean by the word sample is each treatment has a sample. So, there are A samples like this, in under each you have, as I mentioned by assumption, n number of observations, and once I find out the sum of the squares of the average difference between the samples, then also I add up the sum of that average of the in sample errors also. So, this total sum has been divided into two components. So, let me, if I am possible, let me give a diagrammatic, because the equations are very easy to understand, but in order to make things a little bit clear. So, what you have? You have the samples. So, how many such samples? A. So, one error is basically between each, and another is basically when you are comparing between the samples. So, there are two components. So, this will be summed up and this will be summed up. So, in this way you very simply find out sum of the squares. The difference between the observed treatment average and the grand average is a measure of the difference between the treatment means, whereas the difference of the observation within the treatment from the treatment average can be due to only the random error. So, there now you are slowly trying to differentiate the errors into whether it is random error or there is basically error inculcated or into the system. So, the previous equation can be written as, I will try to now use a color and the ink color being changed, is basically the sum of the squares has two parts. The sum of the squares for the treatments and the sum of the squares for the so called the errors. So, this SS suffix treatments is called the sum of the squares due to the treatment, that is between the treatment, and SS suffix E is called the sum of the squares due to the errors. So, the errors have would have an effect on the sum of the square, which is SST. So, that is basically SSE. So, here SST has been divided into two parts, SS treatment, SSE. So, this is the white noise so called coming from the example. There are levels of factors and a treatment means. So, SS suffix T has a minus 1 degrees of freedom, because you are losing 1 degrees of freedom corresponding to the fact. Now, this would make sense based on all the 7 lectures which you have done till far about the information about the variances being not known. Finally, there are n replicates within any treatment providing n minus 1 degrees of freedom. In each case it is reducing by 1. So, technically if I want to find out, so n degrees of freedom with which to estimate the errors, but because there are a number of treatment, hence in each case reduction is 1. So, now if I try to find out the total number of degrees of freedom being reduced, it will be A. So, hence it will be AN, total number of observations, minus A. So, that is basically given by capital N minus A, because we know capital N is basically sum of all the number of observations. So, in each row you have N, how many such rows? A's, you multiply them and find out capital N. So, sum of the square of errors divided by its degrees of freedom, which is capital N minus A, is a pooled estimate of the common variance within each of the treatment. If there were no differences between the treatment, we could use the variability variations of the treatment averages from the Gantt average to estimate sigma square. So, sigma square can be found out accordingly. So, SS treatments is given by the formula, which is the difference between the averages which is happening in the sample and how many such etchings which you have, etchings of the experiment which you have, which is A in number, minus the grand average, which is y bar dot dot corresponding to the sum of all etching and all the samples. The quantities which you find out would be basically be the mean square of corresponding treatments, and the mean square for the errors would be given by SSE suffix capital N minus A, and the mean square for the treatments would be given by SS treatments divided by A minus 1, which is the degrees of freedom which we have. So, they are called the mean square. We now examine the expected values of this mean square and do our studies accordingly. So, the mean square for the values for the mean of the errors would be sigma square, and mean square for the treatment would be sigma square plus a factor which is n summation of the tau square divided by A minus 1. So, thus mean square of the errors estimates sigma square, and if there is no difference in the treatment, which is the means, which implies basically tau suffix I is 0, while mean square of treatments also estimates sigma square. However, note this, that if the treatments mean do differ, the expected value of the treatment mean square is greater than sigma square, corresponding to the fact that the second term which you have may not be 0. A test of the hypothesis of no difference in treatment means can be performed by comparing the mean square of the treatments and the mean square of the error. So, if there is some difference, obviously the second component which I have just highlighted in the red may be not 0 or may be 0, depending on what is your hypothesis are. So, let us see how this can be done. So, you have assumed that the errors epsilon ij are normally and independently distributed between mean 0 and the variance sigma square, and I did mention time and again, I will mention again here that the errors are independent of each other. Thus, the observations yij are normally and independently distributed with mean mu plus tau y. So, tau y is basically the fluctuation which is happening between the mean of any treatment with respect to the grand mean. Then the variance is sigma square, thus the sum square of t, the treatment is the sum of the squares in a normally distributed random variable. Consequently, it can be shown that SS suffix t sigma square is distributed at chi square. This is again, if you do remember, I did mention that the normal distribution concept has a very unique property, that the mean value of the sample and the variance of the sample, which is the square of the standard errors, are independent of each other. And obviously, you will have the chi square when you are trying to compare something to do with the standard error square with respect to the sigma square of the population. So, here it is basically a chi square with n minus 1 degrees of freedom. It can be shown that the sum of square of the errors divided by sigma square is also a chi square with n minus a degrees of freedom, and that SST sigma square is a chi square with a minus 1 degrees of freedom. So, all this would be following up considering that the independence factor which I did mention degrees of freedom. So, hence if your null hypothesis tau I is 0 is true, so obviously they can be an alternate hypothesis where it is not true. However, all the three sums of squares are not necessarily independent, because SST and SSE and SS capital T may not be independent, because the reason is very simple, because SS suffix treatments plus SS suffix errors is equal to SS suffix the total. If the total hypothesis of no difference in treatment means is 0, then the ratio would be given, which is basically, now when you are comparing the variances, again coming back to my repeated statements which I did mention till the fag under the 7th class is something to do with the comparison of the variances, then you will definitely try to utilize the F distribution with a certain degrees of freedom. So, this is what is again happening. You have the F distribution where you compare the mean square of the treatments divided by the mean square of the errors. So, it is distributed with F degree distribution with errors being A minus 1 and capital N minus A. The previous equation is the test statistics for the hypothesis of no difference in the treatment means we should reject H naught and conclude that there is no difference between the treatment if the value of f value which I find out. So, if you remember, if there is no difference less than greater than type, I will try to draw a graph which is a symbolic way of trying to represent for the f distribution, because you remember the f distribution is not symmetric. So, on this part it will be less than type, on this part it will be greater than type, and any error, any value in between would be not equal to. So, based on that the f distribution would be done accordingly. So, if you remember the corresponding the hypothesis testing for less than type, greater than type and not equal to are basically coming from the same fact what we have discussed for the first 7 classes, where we did go into the details about the probability statistics and the corresponding point estimation and hypothesis testing. So, continuing reading, we should reject H naught and conclude there are differences in the treatment if F naught, that is under null hypothesis, is greater than F. Alpha is basically the degrees of freedom, and this would be, and remember alpha, it is not 1 minus alpha by 2 or alpha by 2. That is a very important point, which again I am saying with apologies, I am repeating it time and again. So, where f suffix naught is computed from the previous equation. So, now we list the formulation to find out the various sum of the squares. So, this is the table which will give you an idea. So, this is the analysis of a variance table on ANOVA. So, sources of variations, if I read it on the first column, they are between treatments, error within treatments, and this is the total. So, between treatments, if you remember, is SS suffix treatments, errors within treatment which is SS suffix C, which is the difference between SST minus SS treatments, and obviously SST would be the sum of both of them. You can double check that the values are coming separately as well as count them together. Then the degrees of freedom, they have been mentioned accordingly. So, for the case between the treatment will be A minus 1, because you are collectively comparing them and you are losing 1 degrees of freedom, and errors within the treatment obviously that you are losing 1 degrees of freedom in each of the treatment, hence it will be capital N minus A, and if you sum them up, total errors degrees of freedom is capital N minus 1. Similarly, the mean squares are found, and if you compare the f statistic less than type greater than type, it is given by the ratios of the mean squares of the treatment divided by mean square of the errors, and it can be done the other way around also. So, illustrate the example of analysis of variance or ANOVA. So, we will return to the first example. Recall that the engineer is interested in finding on the power setting affecting the H rate. And he or she runs a completely randomized experiment with respect to the power and the 5 replicates which are being done for each power. Powers are what? 160, 180, 200, 220, and each has basically 5 samples under them. So, those values are given in the table. So, the table has the first columns are the powers, the second, third, fourth, fifth, sixth are basically the reading numbers in a matrix, and the totals are given in the second last column. So, if you add up the row corresponding to 160, that means add up 575 plus 542 plus 535 plus 539 plus 570, you have a value of 2756, the average of which is given in the last column, which is y bar I dot. So, it becomes 551.2. Similarly, you find out all the averages, find out the averages of these averages, which is comes out to be 617.75, which is here, and the average of the and total sum is basically this 12,335. So, from this, if you find out the sum square of total, you basically add them up, the value comes out to be 72,209.75, as sum of square of the treatment comes out to be 66,870.55. We can compute the f value comes out to be 66.80 by finding out this the ratios and compare this to the appropriate upper tail percentile depending on whether it is right hand side or left hand side, which is f 3 comma 16 depending on the degrees of freedom. To use a fixed significance level approach, we do that. Suppose that the experiment has selected alpha is equal to 0.05 depending on the level of confidence. So from there we find out f0 as coming out to be 66, as to be f0 coming out to be 3.24. So as 66.0 is greater than 3.24, we reject H0 and conclude the treatment means differ, that is the power settings significantly affect the mean of the H rate. So how we found out these values? So they are very clear in this table. One can have a look. What I am basically trying to highlight, based on that experiment or that analysis can be done. Usually these calculations would perform on a computer using a software package with the capability to analyze the data. The ANOVA is summarized in the corresponding table. So note that the power in between the treatment means is many times larger than within the treatment errors. So this indicates that is unlikely that the treatment means are equal. More formally, we can compute the values as I read. So continuing that, so the power settings significantly affect the mean each rate, H rate. We can also compute the values of p values for the test statistics and do the corresponding test accordingly. So these are the tables which I have: ANOVA for the plasma H experiment, the sources of variations, the powers are given, are the sum of the squares is given 66 and 870. I am not talking about the decimal values. The errors are given 5339. The total is given, addition of that is 72209. Degrees of freedom are corresponding to 3, 16 and 19. Sum of obviously 3 plus 16 is 19. Mean square are given for power, which is basically the H factor or the value corresponding to A, because you remember I had that here A was 5, 160, 180, 200, sorry 4, it is 160, 180, 200 and 220. So the mean square is 22,219. Again I am not mentioning the decimal. The mean square corresponding to the errors, which is E, is 333. The F value, if not, it comes out to be 66.8, and obviously we take the decisions accordingly. So the reference distribution based on which we drew, and if I remember I did draw a distribution. So here it is. This is the F distribution. The F values are given. So the reference distribution F3 by 16 depending on the degrees of freedom for the test statistic F0 is given, and basically based on that we reject or accept that. And obviously the answer would change if somebody is not, if you basically frame your H0 accordingly. So with this I will close this lecture, and thank you very much for your attention and being a part of this NPTEL MOOC course. We will continue discussing the NPTEL and later on in the lectures in the 10th and so on and so forth. Have a nice day. Thank you very much.